Hi everyone, we are Shangting and Zhichao, and today we're going to give the presentation on our capstone project, Consistent Multiview Color Correction. This project is sponsored by the Facebook Reality Lab, and our advisors are Professor Masu from SMU and Drs. Thomas and Kevin from Facebook Reality Lab. We will first give the brief introduction about the motivation about our project and also talk about the problem formulation. And then we will talk about two parts in our project pipeline, the color checker detection and the color correction. So the background of this project is that the Facebook team is trying to build a VR system that enables people to communicate remotely as if they are face-to-face. So basically, they will render some realistic human avatars and display it on each other's VR headset. And this is how the system looks like. There will be two persons, a transmitter and a receiver, and the sensor will sense what the person is doing, and the encoder will encode the information into a codec. And then the decoder of another person will decode such information, render it, and display it in the VR headset. And our project mainly focuses on the decoder part. So as I just mentioned, the decoder will take the code contains person's information and also the viewpoint information as the input, and it will output the geometry and the texture of the person. The render layer will render the corresponding image. So the decoder is actually trained by minimizing the distance from the real images, pixels, and the render images. So to train such encoder, it actually requires us to get a lot of training data. As the figure shows, the training data contains human faces from different viewing angles. And in order to obtain such training data, the team built a camera capture system called MSCV. So the person will sit in the middle of the capture system, and the cameras all around will capture the human's face from different viewing angles. But there is some problem for such capture system because the images are captured with different camera properties and at different sessions. This will cause the color inconsistency across cameras and across sessions. So we hope that we can do a consistent color correction to correct the image colors of those already captured images. So why it is challenging to correct do the color correction in the multi-view setting? Because actually in the single view setting, we can just calculate the color transform by minimizing the distance from the transformed color and the reference color. The reference color is just a constant number provided by the producer of the color checker. And but in the multi-view setting, the reference color is actually affected by three variabilities. First, the camera variability, which means that the sensors of different camera may sense the color differently. And the lighting variability, which means that the color could be different under different lighting conditions. And this example shows a non-uniform lighting on the color patch. We can notice that those areas have different lighting conditions. And the view variability, which means that the color may be different if we view an object from different viewing angles. So that actually the color correction is entangled with those three different variabilities, which prevent us from the consistent color correction. So that's why multi-view color correction is more challenging. So this is our project formulation. With the color checker images, we aim to estimate the color transform T without confounding the camera lighting and the view effects. And then we can apply such transform to the linear sensor images to get the correct sensor images. And then I will talk about the color checker detection part. We're doing this part because we want to localize the color patches on the color checker. And some existing approach will use traditional image processing based method. So the general idea is that we first find as many quadrilaterals as possible and then register well the color similarity. But the problem of the existing method is that it's not robust. As we can see, it may generate some inaccurate estimation of the patch size and then lead to the inaccurate quadrilateral extraction. And also it has imperfect alignment with the border, and this will cause accumulated error in the distance patches as it shows. And this is especially problematic since we are dealing with 10 by 14 patches instead of 4 by 6 as shown in the figure. So that's why we want to find a more robust method to solve the problem. Actually, we treat each corner of each color patch at the key point, and we want to do the key point detection. So there are three mainly advantages of using the key point detection. The first one is the feasibility, because the key point detection is already successfully used in many complex scenarios like the human key point detection. So we believe this method can also work in our project. And also because we are dealing with data with a lot of occlusions, and the key point detection can also give us a reasonable result in this case. And since we're doing the detection in multiview setting, we can further use some geometric refinement to refine the result. So what's the main bottleneck for us to do the key point detection? It's that we lack of annotated data. So that's why we propose to use the synthetic data to train such a key point detector. So first, we just do some basic data augmentations like random viewpoints, random background images, and the color jitter. But after we test the model on our data set, we found that it just gave us some random output, and it is overfit to the unrealistic texture. We can notice there is still a large texture gap between the synthetic texture and the real texture image. So therefore, we'll propose two solutions. The first one is the global color transform, which means that we multiply each RGB channel with a random number. And the intuition is that we want the network to learn from the relative color values instead of the absolute color values. And the second solution is we replace the synthetic texture with the captured real texture. So after doing those two things, we found that the result is better, but it still has some failure cases when the occlusion exists. And we think that this is because the network overfits to some undesired priors. For example, it used some border clues, or it assumed the color checker is a perfect plane, but actually it's not always the case. So that's why we continue to do some augmentations. The first thing we do is to add some occlusions in front of the color checker. And the second thing we do is to do the elastic deformation to bend the color checker a little bit. So after those augmentations, we can notice the result is pretty accurate and robust, even if the occlusion exists. And even if we zoom in, we can still notice accurate alignment. And also we do a quantitative analysis of the augmentations. We can see that after adding those augmentations, the average key point error reduced from 11 to 2.5. And then we'll talk about how we do the geometric processing to further refine the results. Since we already have a key point detector, we can for the single view setting, we can use the SOPNP method. So basically, we first calculate the camera pose and then reproject the points to 2D. And these are two video demos that shows our prediction results. And those videos are frame-by-frame predictions without the temporal information. I think probably there are some problem with the videos, but actually the result is pretty robust even under some different lighting conditions, and even if the occlusion exists. I think maybe you can check our website. We also put the video demo on the website. So for the multiview setting, we use the triangulation for the refinement. So in PNP, we actually assume the color checker is a perfect plan. So they actually has some error when there are some outliers. But in the triangulation method, it doesn't assume such, doesn't have some such assumption, and we can notice the key point detection result is very accurate. So to summarize, we found that training key point detector on synthetic data is effective for the color checker detection, and for the further refinement, we can solve a PNP or use triangulation. And then Zhichao will take over.
Well, let's move forward to the color correction part. First, let's recall our problem formulation. We are given a collection of color checker images, which we can use to learn a color transform. The color transform is applied to the linear sensor images thereafter, which gives us the images with corrected color, as you are seeing on the right. We hope that we can estimate the color transform without confounding the camera, the lighting, and the view effects. So first, let's look at a standard approach. We have some assumptions to make our life easier. First, since we are doing the color correction in the linear color space, we parameterize the color transform with affine transformation. And also, we only consider the camera variability here, but ignoring the lighting and the view effects, which means we independently estimate the affine transformation for each camera. So for more details, we let someone hold the color checker and stand in the system, and we take an image. This is a color checker image you are seeing on the left. We run our color checker detector over it, so we can sample the color values from each individual patches from this color checker image. Then we solve an affine transformation by minimizing the distance between the transformed color compared with a set of reference color values. During test time, it's straightforward. We have the input linear sensor image. We apply the color transform, which is a affine transformation here, and we do the gamma encoding, and which produces some visually pleasing images on the right. Here is some results for the human face images from left to right. Is the sensor image in the linear color space, the sensor image after gamma encoding, but without color correction. The corrected image, but without gamma encoding, and finally the corrected image after gamma encoding. So simply comparing the second column and the first column, we can see the importance of doing color correction. It can give you some more natural color values. And of course, there is some limitations of the standard approach since we have some very simple assumptions which may not hold. So what's the cost? We can see after color correction, the colors by different cameras looks not quite consistent actually. It fails to disambiguate the lighting and the view effects during the color correction process. And that's why we can see the inconsistent color correction here. So we aim to take another perspective, an inverse rendering view of solving this problem. Inverse rendering is the problem of estimating one or more of illumination, reflectance properties, and the shape from observed appearance, which is one or more images here. So how can it help our color correction objective? First, let's just ignore the sensor effect or the color correction model, and we try to formulate a standard inverse rendering problem. Our input is a collection, our observation is a collection of color checker images, and imagine that we have a renderer. The renderer takes the albedo of the color checker, the normal vector, and the environment lighting as input, and it produces a rendered color checker. So we can optimize the rendered values towards the observation we have. And in that way, we can try to find underlying variable, the albedo, the normal vector, and the illumination that can explain the observation best. So in this way, the environment lighting is shared by different cameras at different time instances, actually. So we can achieve the consistent illumination estimation here. But definitely, we do not consider the sensor effects here, which is the remaining ingredients we aim to add. And here it's very simple. We just apply the color correction model after the rendered values. That is, we have the albedo, the normal vector, and the environment lighting. We do the rendering. We apply the color correction, which is still a fine transformation here, and we optimize it towards the observation, the color checker images. So since we have done the color checker detection, we have the geometry of the color checker, so we know the normal vector. We can use the reference color of the color checker, some standard values under a standard D50 lighting, which we can use it as an albedo. And definitely we know the input image, the observation here. So the only unknown variable is the environment lighting and the color correction model. So we try to optimize this objective so we can jointly estimate the color correction together with lighting parameters. During test time, it's very simple. We just apply the inverse of the color correction model we have here and apply it to the arbitrary input sensor image. That gives us a color corrected image. The remaining thing is the illumination model or the renderer that we use here. So here we are using the spherical harmonics-based illumination model. We assume the environment is Lambertian and the incoming radiance only depends on the surface normal. We have something like this. The shading equals the element-wise product between the albedo and the sum of the lighting weighted by the spherical harmonic spaces. The spherical harmonics function takes the normal vector as input, and we can understand it as a basis of function that you can use it to approximate arbitrary real valued functions defined on the sphere. So now let's look at some results here. We can see some improvement on the view-dependent effects. To illustrate this issue, we place a small patch of rendered color inside each image patch to show how well the estimated lighting and the color correction consistently explain the observation. So it would be best if you cannot tear the rendered color within each patch, but I think it's not the case. I mean, for the left part, which is the result of the standard approach, we can see sometimes for some parts, it might, the render value might look pretty similar to the background color, but sometimes it's not the case. This is caused by the failure to consider the view-dependent effects. But we can see the improvement by the inverse rendering-based method, which we are showing on the right. We also do some quantitative metric. We compute the average distance between the rendered color and the sensor image computed across different cameras and time instances. We can also see some problems caused by the spatial lighting effects. Here is the result of a standard approach. An example, on the left is a sensor image, and on the middle is, again, the rendering. We place some rendered value within each small individual patch of the observation, and which is the same as the previous slide. So we can see sometimes, for example, for the middle row in the yellow box, the rendered value looks pretty close to the background, but it's not the case for the bottom row, as shown in the blue box. We can see the contrast is not consistent. This is caused by the non-uniform lighting across different spatial locations here. So let's recall our the inverse rendering problem that we formulate. We use the spherical harmonics based illumination model where we have gamma here is lighting parameters, but it's global. So it cannot represent a spatially varying illumination. How can we change it? It's very simple. We just define a 3D grid of the lighting parameters, and for every spatial location, we try to slice a gamma from that grid, and then we can do the forward rendering and optimize it towards the observation. So let's look at some comparison. And still, this is a result by a standard approach. And this is the result after introducing the spatial lighting variability. We can see this time, just comparing these two pages, we can see better consistency in terms of the contrast, I mean, between the rendering and the observation. And finally, we can see some better consistency by our method. Here, we can observe the better consistency after color correction. But of course, here the result might look dimmer, but it's because the scale ambiguity between the color correction model and the lighting, and it can be addressed by white balancing, which we didn't do here. So to summarize, the standard approach disregards the view and lighting effects, and it can lead to inconsistent color correction in a multiple view setup. We can solve an inverse rendering problem via jointly optimizing the lighting with color correction, and it proves an effective direction. As a future work, we aim to explore more expressive illumination and color correction models. Yeah, and that's all we have today. And thanks for your attention. And we're happy to take any questions. Yeah.
Thank you very much. So let's take some questions from the reviewers. I think we have Giannis and David here today.
Yeah, I had a couple of questions. First of all, a very good presentation. Good job. So first of all, I don't know if I missed it. When you parameterize the illumination with spherical harmonics, how do you introduce color there? Do you do 3 spherical harmonics per channel? Each channel has its own spherical harmonics?
Please wait a second. Do you mean the degree of freedom of the or the dimension of the lighting coefficient? Here, the lighting coefficient, the gamma is a scalar actually, which is the same for the RGB channel.
So wouldn't you need to also take into account the color of your light source to be able to do fully accurate color correction? Meaning that you would need to basically make the gamma M be a 3x1 vector.
Yes, yes. We tried it, but sometimes it can introduce some. I guess it will introduce some ambiguity. I mean, between the factor that you just mentioned and between the color correction, I guess, because we were left multiplied with the color correction within a fine transformation.
I see.
And of course, we also experimented with both actually. I mean, the 3-dimensional and the 1-dimensional. But in terms of the result, we didn't observe a very obvious difference. I mean, in terms of the rendered performance, yeah, the render quality.
But all of these, was all of your inverse rendering done under inverse illumination using the same lighting, like same kind of lamps, for example? Because if you were to go, I guess it doesn't matter so much for the application you care about, but if you were to do the same inverse rendering outdoors at noon versus indoors with LED lights, those have pretty different spectra. So I'm guessing that you wouldn't be able to get very consistent results without taking into account the color of the light source.
Yeah, that's a good point. Yeah, actually, here we assume, I mean, the environmental lighting isn't changed a lot across different time instances. Actually, yeah, we assume it's always performed in the MSCV system.
Okay.
The indoor, yeah.
And then I think it's slide 51. You did hint towards that in the end. This 51. Can you go to slide 51? Yeah, so don't you need to use any priors for this optimization? Because you have this product ambiguity between alpha A, the color correction, and the rendering. And if you try and optimize for both, it seems to me that you would end up with a very unstable, non-convex, and sensitive to initialization optimization problem. So my 2 questions here were, how do you initialize this to make sure that you end up with a good solution? And second, yeah, don't you need to use any priors to avoid ambiguities?
Yeah, first, I mean, the only optimizable variable here is just the affine transformation and the lighting parameter. For the affine transformation, we initialize it with identity transformation. And for the environmental lighting, we just initialize it with constant 1. Yeah. And of course, I can totally get your point. I mean, there is lots of ambiguity we didn't enforce. For instance, I mean, the scale ambiguity. I mean, if we multiply the matrix A here with arbitrary real value and we divide it, I mean, by the multiply the lighting parameter by that value, the loss is the same, and that's why we can see the result on this page. I mean, it looks dimmer here. Yeah.
Okay, but in practice, this ambiguity that exists here didn't seem to affect your results, which is just getting a color-corrected image very much, is what you're saying.
Yeah, actually, I think because the objective of this project is to do the color correction, right? And here we are, here we include the lighting estimation as well, and it's just out of the purpose to, I mean, to handle the view-dependent effects, the environmental lighting effects. That's why we include it here. So we jointly optimize this to try to explain the observation we have best. So in terms of the, I mean, the metric or the qualities that we try to assess, I mean, in terms of this solution, and it's just in terms of the rendered results compared with the observation, but it doesn't indicate that, I mean, if we decompose the color correction and the lighting, the environmental lighting estimation, and if we view them independently, they are perfect. I want to say that. Yeah.
Okay. And a quick question about the first part. You said that, if I remember correctly, you draw random color lighting vectors for your training, right? Would it help your learning algorithm if instead of just drawing random vectors, you drew them from some distribution that corresponds to realistic, to the distribution of colors in realistic lighting environments? Say if you took, for example, a bunch of environment maps from outdoors, did PCA on them, and then sampled color vectors based on that PCA distribution.
Can I see your question again? I'm sorry.
So I was saying that you create a training set by just sampling random color vectors. So all I was asking is whether it would help improve the performance of your learned model if instead of creating a training set with completely random colors, you sample them based on some distribution corresponding to realistic illumination environments. Like our illumination will not be any arbitrary color in general. It will correspond to various hues of white and off-whites corresponding to colored lamps. So you can learn those. You can learn distribution for those by simple example, taking 1,000 environment maps from online, doing some PCA on that, and then sampling from there. So would that make your learning performance better?
Yeah, that's a good point. Yeah, I think I think it will make the generation process more realistic and more close to the real world scenarios. And yeah, we didn't consider it. Yeah, and we would expect it to help. And our motivation here using some random color is just we want the color checker to focus more on the relationship, or the relative color when we compare different patches. We don't want it to focus on the absolute value of the color. So even though the generated color might not look very realistic, maybe for this example here, but it can still tell you that it doesn't affect you. I mean, it doesn't prevent you from predicting a correct key point, right?
Yeah, I want to add something here. I think the thing we want to do here is to avoid the overfitting. Like, for example, when we detect the color checker, we need to know which point is the first point that like what key point is, which key point is corresponding to which kind of color. So if the color change, we want such kind of correspondence still exists. So that's why we do the color transform here, I guess, to prevent the overfitting.
Okay.
Let's have one question from David, and then we'll wrap it up.
Yeah, thanks. Actually, I just have a pretty small question. So I guess in this slide, it looks like the corners are white, but in your other pictures of color correction, they're always green tinted. Is there a reason for that?
Do you mean just for the white patches?
The corner, yeah, like in this example, the corners look green tinted, and in the other original images, they looked white.
After color correction, we should expect it to look white, but the reason why I mean the white patches looks greenish is because we do not perform color correction, and that's the purpose of this project actually. Yeah.
Can I see the image after color correction?
We have the color correction image tested on the human face images, and
I see.
but we didn't perform it. I mean, because here, I mean, for this part, in our previous slides, we have that result, but here we're treating it as a rendering problem, and the fine transformation is actually the inverse of the actual color correction that you apply to the image. So you should apply the inverse transformation of the sensor image on the left here. You get the corrected image, but here we are placing some small patches, the albedo, multiplied with the inverse of the color correction. Yeah, so this is a rendered results.
Oh, okay. So you didn't visualize the color corrected.
Yes. Yeah.
I see. Okay. Got it. Yep. Thanks.
Thank you very much. And then thank you for the presenters and the reviewers. We'll start the next presentation now. And as soon as you're ready,